Have you ever wondered what makes a substance a strong or weak electrolyte? Let's dive into this fascinating world of electrolytes. Essentially, electrolytes are substances that, when dissolved in water, break up into ions, which are charged particles. These ions allow the solution to conduct electricity. Now, the strength of these electrolytes depends on how completely they ionize in water. Strong electrolytes like table salt or sodium chloride break down completely into ions when dissolved in water. These solutions are excellent conductors of electricity. On the other hand, weak electrolytes, such as acetic acid, only partially ionize, forming fewer ions and hence conducting less electricity. In essence, the degree of ionization determines the strength of an electrolyte. A higher degree of ionization equates to a stronger electrolyte. But remember, not all substances are black and white, strong or weak. Some sit in the gray area in between. Remember, the strength of an electrolyte depends on its degree of ionization. Now that we understand electrolytes, how does ionization work with polybasic acids? Well, let's unravel this together. Polybasic acids, unlike monobasic ones, have more than one ionizable hydrogen atom. This means they can lose more than one proton during ionization, leading to the formation of multiple ions. Take sulfuric acid, for example. It's a dibasic acid, meaning it can lose two protons. Its ionization happens in two stages. In the first stage, it loses one proton to form the hydrogen sulfate ion. In the second stage, it loses another proton to form the sulfate ion. Fascinating, isn't it? But what about acid strength? Well, acid strength is tied to the degree of ionization. The more an acid ionizes, the stronger it is. So the stronger the acid, the more it ionizes. Hence, sulfuric acid, which completely ionizes in water, is a strong acid. So the stronger the acid, the more it ionizes. But how can we measure the acidity or basicity of a solution? Enter the concept of pH, a measure of the concentration of hydrogen ions in a solution. The term pH literally means power of hydrogen. You calculate pH as the negative logarithm to the base 10 of the molar concentration of hydrogen ions. This means if you have a higher concentration of hydrogen ions, your pH value will be lower, indicating a more acidic solution. Conversely, a lower concentration of hydrogen ions results in a higher pH value, pointing to a more basic or alkaline solution. The pH scale ranges from 0 to 14. Solutions with a pH less than 7 are acidic, while those with a pH greater than 7 are basic. At pH 7, we find pure water, perfectly balanced in acidity and alkalinity. Common examples can help us visualize this scale. Lemon juice, for instance, has a pH of about 2, while baking soda sits around 9. Thus, pH is a simple yet powerful tool to measure acidity or basicity. What happens when salts interact with water? Well, this process is known as hydrolysis of salts. In this reaction, a salt reacts with water to produce either an acidic, basic, or neutral solution. If the cation or anion of the salt is the conjugate acid or base of a weak acid or base, it will undergo hydrolysis, altering the pH of the solution. For instance, if we take ammonium chloride, a salt of a strong acid and weak base, it undergoes hydrolysis to form ammonium hydroxide and hydrochloric acid. The solution becomes acidic. Conversely, a salt of a weak acid and strong base, like sodium acetate, forms acetic acid and sodium hydroxide, resulting in a basic solution. Now, let's delve into buffer solutions. These are special solutions that resist changes in pH when small amounts of an acid or base are added or when the solution is diluted. A buffer solution contains a weak acid and its conjugate base, or a weak base and its conjugate acid. Imagine you're making a delicate dessert that needs a specific pH to set. A small change could ruin your dessert. That's where a buffer solution comes in. It ensures that the pH stays stable, even if you accidentally add a bit more of an acidic or basic ingredient. In a nutshell, buffer solutions help maintain pH, a crucial aspect in many biological and chemical processes. Scene script. How can we quantify the behavior of buffer solutions and solubility? The answer lies in two vital concepts: the Henderson equation, and the solubility product. Let's start with the Henderson equation. This equation is a simplified expression of the law of mass action, which describes the behavior of buffer solutions. It's a relationship between the pH, pK, and the ratio of the concentrations of a weak acid and its conjugate base. In essence, the Henderson equation allows us to calculate the pH of a buffer solution based on these variables. It's a crucial tool in our chemistry toolkit, helping us understand and predict how buffer solutions will behave. Now, on to the solubility product. This is a measure of a compound's solubility, how much of it can dissolve in a particular solvent. The solubility product, represented by the symbol K-SEP, is the product of the concentrations of the ions in a saturated solution of the compound, each raised to the power of its stoichiometric coefficient. By knowing the solubility product, we can predict the maximum amount of a substance that can dissolve in a solution under a given set of conditions. This, in turn, can help us understand how substances interact in various chemical reactions. These equations are essential for understanding many chemical reactions and processes. They are not just mathematical expressions, but the keys to unlock the mysteries of chemistry. Ever wondered how adding a common ion affects a solution? Well, let's dive into that. This phenomenon is known as the common ion effect. In essence, it's the effect on equilibrium when an ion in common with the ions in a solution is added to that solution. Consider a saturated solution of silver chloride, AgCl. This compound partially dissociates into silver and chloride ions. Now what happens when you add a dash of sodium chloride, NaCl, which also dissociates into sodium and chloride ions? The extra chloride ions from the NaCl suppress the ionization of AgCl. This happens because the reaction is trying to maintain equilibrium, so it shifts in the direction that would reduce the excess chloride ions, leading to the formation of more HCl. This is the common ion effect in action. Let's take another example, this time with a weak acid, acetic acid. When it dissociates, it forms acetate ions and hydrogen ions. Add some sodium acetate into the mix, and you've got a common ion, the acetate ion. The presence of these extra acetate ions suppresses the ionization of acetic acid, reducing the concentration of hydrogen ions and thus increasing the pH of the solution. It's important to note that the common ion effect is a direct consequence of Le Chatelier's principle, which states that a system in equilibrium will adjust to counteract any change in conditions. In this case, the system is the ionized and unionized forms of a substance, and the change is the addition of a common ion. The common ion effect has practical applications too. It's used in processes ranging from the precipitation of salts from a solution to controlling the pH of solutions in industrial processes, and even in our bodies to maintain the pH of our blood. So there you have it. The common ion effect is a fascinating aspect of chemistry with practical applications. So, we've covered a lot of ground today, haven't we? We've journeyed through the world of electrolytes, dove into the depths of ionization, and even scaled the heights of pH. We've unraveled the mysteries of hydrolysis, buffer solutions, and the Henderson equation. And we've discovered the wonders of solubility product and the common ion effect. All these concepts are crucial building blocks of chemistry. Thanks for watching. If you found this video helpful, give it a thumbs up, share it, and don't forget to subscribe to Facts Academy 0122. Leave your comments below. We'd love to hear your thoughts.